Let's see. The last class we discussed about how the Arrhenius equation, which was empirically derived, was identified for rate constant. It has two important parameters. One is pre-exponential factor. The other one is uh, activation energy. And both of these are independent of temperature. Using that knowledge, we were able to derive how rate constant at different temperatures. This is at same temperature, but for different scenarios, which is with and without catalyst. Then for different temperatures, we got this scenario, which is very similar to that of Van 't Hoff's equation. And we noticed that a Maxwell-Boltzmann's curve, how we discussed for gases, the same thing can be identified here. It is about number of fraction of particles which have a certain kinetic energy. If you plot that for various kinetic energy factors at a constant temperature T1, then this is how the graph looks like. And for T2, this is how it looks like. And this is that particular temperature. This is that particular energy, which we call it as activation energy. Crossing this activation energy, reactants can convert into products. So using this graphical fact, we did understand one thing, that in most cases, if the temperature difference is 10 units, right, then the rate of increase of rate, the increase in the rate would be 2 to 3 times. And that amount of increase of rate is what we call it as temperature quotient. Got it? So you can see for 300 to 360, we learned that 2 raised to power of 6 times it will be raised. And from there, we got a general formula that mu raised to power of delta t by 10, that is equal to k plus t, k of t plus delta t by kt. Okay. So this helps us figure out, how much will be the increase in temperature, how much will be the increase in rate of the reaction. Now, this was more empirically derived. Theoretically, we can also derive a similar formula using collision theory. Imagine there is a bimolecular collision as in two molecules colliding with each other. Okay. So assume if two different molecules are colliding with each other, then the rate can be expressed as some constant into a raised to power of x and b raised to power of y, where x and y is the uh, order of the respective order with respect to reactants, and x plus y is the order of the reaction. Consider this is an elementary reaction. Well, if it's elementary reaction, then the order will be 1 and 1, which means it is a second order kinetics. Okay. And now, in general, the rate is always directly proportional to number of collisions happening per unit time and per unit volume. Okay. Which makes sense, right? Because if you have more number of collisions only, chances of forming the product would be more. Therefore, so rate would be always proportional to concentration terms. Okay. That is rate will be proportional to number of collision terms. Now there are multiple type of collision factors if you could recall. One is collision frequency, which we represented by Z11 or Z11. Okay. If you may recall, there was one definition which is collision number. Okay. Collision number. Collision number usually represented as Z1. Z1 basically represents collisions, number of collisions made by number of collisions made by uh, a particle, one particle, okay, in unit time. In unit time, how much number of collisions one particle is doing, that represents collision number. Now what is collision frequency then? Collision frequency is the number of collisions done by all the particles. Now imagine I have n number of particles here, correct? And let's say there are z1 number of collisions made by each particle. Each particle is making z1 number of collisions. Then total number of collisions will be how many? Z1 n by 2. Why these two? Because with respect to particle 1, if you count there are z1 number of collisions, then definitely with respect to particle 2, 1 2 collision or 2 1 collision is same only, right? Therefore, with respect to every particle when you count, right, there will be always one duplication. Hence, so total number of collisions is Z1 n, which is theoretically these many number of collisions should happen, but divided by 2 will give you all the unique number of collisions happening. So Z1 n by 2 is the total number of collisions happening per unit time. But collision frequency is a definition which suggests it is number of collisions per unit time per unit volume also. That's why it divided again by volume. So there is that small difference between these two. One is this is only per collision number is only per unit time. Collision frequency is per unit time and unit volume also. Okay. Hence Z1 n by 2 divided by V, that gives you collision frequency. Now Z1, when we calculated using the bimolecular collision theory, we found that Z1 is equal to this value, that is root 2 pi sigma square. Sigma is the collision diameter. Collision diameter means if a particle is like this, okay, and when it is colliding with the other particle, then the amount of distance between the centers is what we call it as the collision diameter. Okay. Well, in case if you have two different particles, suppose if you have this as A and A, then it is fine. But what if you have two different sizes? Okay, or two different particles only? In case if you have two different particles, A and B, then we take something like an average here, okay, which we call it as AB. And that AB can be calculated as average in terms of their squares. So sigma A square plus sigma B square by 2 is equal to sigma AB square. Okay. And U average. If you are talking about the same particles, then the U average value is 8 RT by pi m. Okay, 8 RT by pi m, correct? But if you have two different particles, instead of taking m, which should be like a average mass, so what we can do, we use this as mu, which is like the weighted average. So that is Ma into Mb divided by Ma plus Mb. These are the molar masses of AB. This is called reduced mass. Mu is called as reduced mass. So UAB will be under root of 8 RT by pi U. Okay. That is average speed. And now N by V is defined as N star. That is number of collisions per unit volume. Okay. Now you see that already there is one N star and now there is one more N star, developed in this equation. That's why when you write Z11, it will be 1 by 2 times of this entire thing, correct, into N by V, which is also N star. So in that entire thing, there is already one N star. So N star into N star will become N star square. And now you can see half pi sigma square U average N square is what you have. Suppose if this N star is with respect to number of collisions of A, number of collisions of B, then I can write that N star square as Na star and Nb star. So this is with respect to bimolecular collisions of two different particles. If the collision is happening between same particles, then this is the formula we use. If they're happening between two different particles, then this is the formula we use. Nevertheless, now you notice UBA average. Now, number of particles can always be written as, you know, uh, this is number of particles with unit volume, correct? So, N divided by V. Now, number of particles can always be written as number of moles into Avogadro's number. So, that's what I have written. Number of moles multiplied by Avogadro's number. Here also number of moles multiplied by Avogadro's number. Okay. I will color the Avogadro's number just to make sure that you don't get confused with this Na. This Na is Avogadro's number. Got it? Hence, now have you noticed something? Na by V is basically concentration of A. Nb by V is a concentration of B. Therefore, ZAB is equal to, these entire things are constant, pi sigma square, clear, root 2, in U average this 8 RT pi, all of these are constant values, right? And that entire thing, if you multiply that, we'll get this as K dash into concentration of A into B. So therefore, if you compare the rate law expression, which is equal to K into A into B, now compare the same thing here also, because rate is basically directly proportional to ZAB. Now, if I put some proportionality constant, that proportionality constant come out to be some F. F is basically fraction of collisions which are effective collisions. That means which can cross the barrier. This we can, you know, fetch it from the Arrhenius equation, that the that the fraction of particles is always equal to exponent to the power of minus EA by RT. Okay. So if I substitute that back, ZAB is equal to this entire thing. So you can notice that Z uh, K1 here, or K dash into F into A into B, that gives you the rate of the reaction. And if I compare that with the original rate law expression, then I can say K dash into this entire thing, correct? That represents your rate log, I mean rate constant, isn't it? So this is a comparison of these two. So K, which is rate constant, this is rate constant. So rate constant K is equal to K dash into exponent power minus EA by RT, which we validated with Arrhenius equation, which is similar to this K dash was similar to A e raised to power of minus EA by RT. So that's how you can see theoretically and practically we get the same thing. But there is one important change here. If you notice, K dash is basically all the constants which we have, right? So 1 by root 2 pi sigma square U average. Now notice U average basically is under root of T into U reduced mass, which means this K dash term is actually dependent on temperature. Hence, as per collision theory, pre-exponential factor is a dependent value on temperature. Unlike in Arrhenius expression, it is said that it is independent of temperature, but here this is dependent on temperature. Everybody clear on this logic? Okay. So these are two important factors we need to understand, that whether it is dependent or independent part. Okay. So go through it for a minute. There are there are few things that we need to understand. Okay. This I would suggest you all write it along with me. Got it? In the notes I have not mentioned. In the pre-notes I have not mentioned this. So check this out. One, what is the significance of that F which I have written? Okay. Sorry. What is the significance of rate which we have written? See, rate actually I have written this as Z11 into F. Correct. And Z11 we found it this as K dash into e raised to power of minus EA by RT, which is the fraction part, into concentration terms. Correct? And this entire thing is what we wrote it as K into concentration terms. But actually, there is one more term that will come along with it. Okay? That is P factor also. Right? So let me write down that here. In many cases, in many cases, theoretical rate, theoretical rate, okay, uh, theoretical rate of reactions is not matching, is not matching, right, with the experimental, with the experimental result, the experimental result. Okay, for such reactions, for such reactions, we can say that rate of the reaction is equal to, just like how we added that Z11 into fraction of particles is minus EA by RT, then I have to multiply one more term known as P. This is also called as the probability factor or steric factor. Is also called steric factor. Got it? So this factor is to be multiplied just to make sure that theoretically and experimentally the result matches the same. Now, how do we need to assess that theoretically what is the value and experimentally what is the value? Okay, so put it this way. If the theoretical value, if the theoretical value, that means the one which we have derived through collision theory, is greater than, is the greater than the experimental value, experimental value, definitely then P has to be less than 1 just to compensate that value, isn't it? So because theoretically we are getting a larger value, so that means that steric factor has to be such a way it should try to minimize that value and try to match it with the experimental value. Likewise, if the theoretical value, if the theoretical value is smaller than, smaller than the experimental value, experimental value, then P has to be greater than 1. Okay, clear? So please do remember, if the P value is less than 1 given, you, what you need to understand that theoretically the value is coming higher than practical value. If P value is greater than 1 given in the question, which means you are getting theoretical value smaller or lesser than the experimental value. Got it? Clear? Right. Now, you might be also asked that we need to prove, or earlier I showed you a graph that how Maxwell's distribution, which is with respect to speed, can also be derived with respect to kinetic energy. Okay. And if we are deriving that in terms of kinetic energy, how does the equation look like? Okay. In certain number of questions, they have actually used that expression. So let us understand how the expression is used. Okay. So let me show you. First, let me put it as a question here. Derive an expression, derive an expression for distribution, distribution curve with respect to kinetic energy. Okay. Let me tell you what is Maxwell's Boltzmann's curve. Maxwell Boltzmann's equation is dn, correct? dn is equal to 4 pi n into m by 2 2 pi rt raised to power of 3 by 2, correct? And then we'll get u square, and then we have exponential value, which would have minus mu square by 2rt, correct? This into du. This was the original expression for Maxwell's Boltzmann's curve. And graphically, how does it look like? If you notice, dn by n du versus u, correct? If we plot this, we will get the curve like this. Sorry, it will have something like a bell curve at a temperature T, constant temperature T. Correct? This is a typical graph which we have. Okay, right? And now, what you know is that kinetic energy can be written as half mu square, isn't it? And you know that in this value, where we write it for one particle here, we know that uh, Boltzmann's constant can be written as R by Na. Boltzmann's constant can be written as R by Na. So from here, can I write that U is equal to, I'll write, see, kinetic energy. I will use this term as E. Okay. So we can write this as E here. So in that case, I can write U is equal to under root of, okay, 2E by M. Yeah. I can replace that value. Got it? So if at all I differentiate this, what do I get? Du is equal to under root of 2 by m, correct? And then again I will get this as half of e raised to power of minus 1 by 2, correct? That into dE. This is what is the expression which I'll get, isn't it? Which can be written as 1 by under root of 2m into e into dE. Can I write that? Clear? Because that 2 and 2 will cancel out as a root 2 there. So we'll get this term. So wherever there is u and wherever there is du, you replace this term. So now I'll get dn is equal to 4 pi n as usual, which will be m by 2 pi rt into, where there is a u square, what do we write? We write this as 2e by m, that multiplied by exponential of, correct, m by, right, 2 pi rt, correct? Because now again that u square will become 2e by m, correct? So that whole raised to power of, clear? Now notice there is one problem here. The m and m are two different factors here. That capital M is a molar mass. This small m is basically mass of one particle, isn't it? Because here we are talking about mass of one particle, kinetic energy with respect to one particle. So basically, this will not be like this. It will be m by, correct, which is minus 2 rt, and that is u square. The u square can be written as 2e by small m. This is what it will become, correct? And what about du? Du can be written as 1 by under root of 2me into de. All good? And now this m factor is what I need to pull it out, because here also there is small m only. This is not capital M. 2e by m. I'll write down that here because that should not confuse the other terms. Small m. Yeah. Okay. Clear? Now if I work this out, so what do I get? 4 pi n, correct? There will be now m, this is 3 by 2. M by 2 pi rt, correct? Whole raised to power of 3 by 2. Okay. Into e raised to power of, now you can notice that here I can write this as e by rt. 2 will get cancelled. That will be e by rt. And if I write this m in terms of mass, then it will be mass into Avogadro's number. So that mass factor will get cancelled. So what do I have? Exponent of minus na. This is Avogadro's number, mind you, into e. divided by 2 is getting cancelled, so RT, this is the value you will be left out with. Okay, that into, now you notice that this 2m and this 2m here, that will get cancelled. I mean, of course, by root times, so we'll get this as root of 2m, sorry, root of 2e, that divided by that mass will be present as 3 by 2 into dE. This is the factor that is left. So this is a formula of dN in terms of kinetic energy. And the same thing when you plot it, this is the same thing which I plotted earlier. So dN by, sorry, n, what is it? dN by n dE versus E. If you plot that, this is how the graph again, which will have almost similar graph like this. This is a temperature T1, and somewhere at this point, you will have activation energy. Clear, everybody? Please go through it once quickly. Check out. And I hope you understood how we derived that. Sorry. Before going further into the application of uh, Arrhenius equation and collision theory, theoretically, the last part that we need to learn is what are parallel and series reactions. Okay, so let me take you through that first, then we can do some problem solving. Both in parallel and series reactions, our assumption is we are going through a first order kinetics. Now, let me tell you what our parallel reactions means. Parallel reaction is when a reactant is giving a product and it has a certain rate constant associated with it, K1, and it has some activation energy, EA1. But at the same time, it is also involving into one more reaction where the rate constant is different, activation energy is different. When the rate are not related like this, or rate constants are not related, then you can't simply write that A is giving B plus C. When you write it this way, then you assume that the rate at which the B is forming and the rate at which the C is forming is same. But that is not the case here. Hence, you have to write it as two separate reactions. A is giving B with a rate constant K1. A is giving C with respect to a rate constant K2. Got it? And now notice, if you write the instantaneous rate equation, then R1, that is the way it is going in forward direction towards A to B. This is for A to B reaction. Then it will be K1 into A. Then A to C reaction, A is losing A is following a rate value of K2 into A. Then the overall rate is basically the sum of rate R1 and R2. This is the overall rate of change of A, which is rate of formation of B plus rate of formation of C. And dB by dt can be written as K1 into A, and dC by dt can be written as K2 into A. Okay. So this A will come out to be common. So K1 plus K2 into A. K1 plus K2 can be written as K resultant or K overall, anything, K average. You can write anything like that. Okay. So this is K overall into A. And if I bring this A to the left hand side, so I will get integral A0 to AT dA by A is equal to K1 plus K2 into 0 to T dt. Okay. And now notice this could be a, after integrating, it will be log value ln A0 by AT is equal to K1 plus K2 into T. Correct? I have compensated this minus by writing A0 above and AT below. And in fact, if I remove the log and make it anti-log, then I'll get AT is equal to A0 e raised to power of minus K1 plus K2 into T. Okay. And T half, you know that it will be 0.693 by K, but here it is about K overall. In this case, it is K1 plus K2 and ln 2 by K1 plus K2. Got it? This is T50. Now, up to this, anything with respect to A is very simple because it's just a first order kinetics. There is not much of a difficulty there. But notice, what if you have rate comparison of B and C, rate of B by rate of C. That is dB by dt by dC by dt. You cancel dt and dt. That will be equal to K1 by K1 into A by K2 into A. A will get cancelled, which is equal to K1 by K2. So basically dB by dt and dC by dt is equal to K1 by K2. That's a constant value, which means if I integrate this also, this will remain constant. So therefore, it will be B divided by C, which will be K1 by K2. So concentration of B at any time with respect to concentration of C at any time will always remain constant, which is equal to K1 by K2. This is a very, very important formula for us. Okay. Now, the third aspect in this case is to figure out what is the concentration of Bt and Ct. Well, we know that At is equal to A naught minus e raised to power of minus k overall into T. Now, come to this factor here. Suppose initially A is A naught amount, then B is 0 and 0. And at time T, let's say A naught lost some X amount to form X here, Y amount to form Y here. Correct? Then can I say at any point of time AT plus BT plus CT, that should be always equal to A naught, right everybody? So you can see AT plus BT plus C naught is always coming out to be A naught. So sum of these three should be always equal to A naught. Okay. So we will be using this factor here. So you know that AT is equal to A naught is equal to AT plus BT plus CT. And CT from the second derivation, we know that CT at any time will be equal to BT into K2 by K1. So that's what we are writing, BT into K2 by K1. No, B will come constant. So I will get K1 plus K2 by K1 plus AT is equal to A naught. So now BT will be equal to A naught minus AT multiplied by K1 divided by K1 plus K2. Okay. And you notice we learned that AT can be written as A naught e raised to power of minus k overall into T into K1 by K1 plus K2. Hence, if I take this A naught constant, A naught common, I'll get this as 1 minus e raised to power of minus K1 plus K2 into T multiplied by K1 by K1 plus K2. This is BT. Now, same thing we can do it for CT also, because this is the same factor which we will be using. And instead of BT, now I'll write in terms of CT. And when you do that, you'll get the same equation just like BT. Only one difference, instead of K1 here, now you'll have K2. Okay. So everybody, this is BT, CT and AT. We already know that as A naught e raised to power of minus K1 plus K2 into T. These three are the concentration terms at any time T. Got it? A lot of times, you would not be asked about the derivation of AT, BT or CT. Instead, you will be asked about identify the fractional yield of B and C. How much is the fraction of B and C? So check out. Fraction of B is equal to how much B is formed with respect to the total products formed. So total product is B plus C with respect to, B with respect to this total will be equal to K1 by K1 plus K2. So the percentage yield of B will always be equal to K1 by K1 plus K2 into 100. And percentage yield of C will be equal to K2 by K1 plus K2 into 100. Got it? I suppose this factor is also clear, everyone. Now notice next one. If I want to calculate the net activation energy of A, this is the next important factor in parallel reactions to figure out what is the net activation energy. And notice K average is equal to K1 plus K2. K average is equal to K1 plus K2. Correct? Now, which is equal to K net or K overall. K net is AN e raised to power of minus EAN by RT. That is net K value, which is equal to K1 plus K2. K1 plus K2 can be written as A1 e raised to power of minus EA1 by RT, A2 e raised to power of minus EA2 by RT. Now, differentiate this with respect to temperature. What do I get? If I differentiate this, AN e raised to power of this entire thing will remain the same, and then we'll enter into the exponential factor here. So if you differentiate this one, you will get EAN by R into 1 by T square with minus. That minus and minus will become plus. That will become plus here. And same thing will come A1, this entire thing. And again, if you differentiate here, so you'll get EA1 by RT square. And here you'll get EA2 by RT square. Got it? And now you can see this entire thing is Kn. This is K1. This is K2. So K1 into EAN is equal to K1 EA1 plus K2 EA2. And Kn is basically overall K, which is K1 plus K2. So if I put that, I will get EAN is equal to K1 EA1 plus K2 EA2 by K1 plus K2. It is like weighted average. Check out carefully. It is like weighted average. K1 EA1 plus K2 EA2 by K1 plus K2. Clear, everyone? So these two factors you need to understand very carefully. First, how to calculate the concentration of B and C. Second, how to get to know what is the exponential value here. Sorry, what is the activation energy value here? Okay. So please quickly go through the derivation for B and C first quickly. Everyone, please check. Check. Let's see. What if you have something like A giving B and C a parallel reaction with K1 and K2? Initial moles of A given is 1 and K1 and K2 relation is given. We need to find out the number of moles of A, B, C at half life. Okay, what would happen at half life? All right. Well, what is the typical things which we need, which we know here? I'll just write on that part. We know that number of moles of B by number of moles of C, which will be same as the concentration of B and concentration of C. That will be equal to K1 by K2, which in this case is 2K2 by K1. K2, that is equal to 2. Okay, this is one thing we know, correct? Secondly, if you notice A giving, sorry, A giving B and C, here this will be A naught minus X minus Y, and this will be X and Y, which means I know that X by Y is equal to 2. X by Y is equal to 2. And what is the other thing which we know? Okay, because X by Y, this Y now, and you know that AT, A naught will be equal to AT plus BT plus CT, isn't it? So therefore, now we can write this X and Y terms, right? Because the ratio here will be X divided by, correct? How much will be the Y amount here? Y amount will be, this will be A naught, right? Minus A naught minus X minus Y. And if I write this B and T term here, that will be basically A naught by 2. Sorry, let me write down directly here because we are talking here for the half life here. So I can say X plus Y should be equal to A naught by 2 for T50. So therefore, this will be equal to A naught minus Y can be written as A naught by 2 minus X. That is given as 2. Hence, X is equal to A naught by 3 and Y is equal to, which is X by 2, that is equal to A naught by 6. Therefore, AT concentration will be A naught by 2 at T50, BT will be A naught by 3, and CT will be A naught by 6. Okay, this is the way we can figure out what are their concentration terms at half-life. Okay, see the next question. A is giving 2B and 3C. Rate constant are K1 and K2 this time. Okay. First, I need to figure out what is the instantaneous rate. And second, I need to figure out what is the ratio of the B and C. Now you notice that rate of A must be equal to rate of formation of B plus rate of formation of C, correct? So that's what I'm writing now. Rate of A, which is minus dA by dt, must be equal to, okay, K1 plus K2, right, into A at T. But at the same time, if you write in terms of B and C, that will be minus 1 by 2, sorry, plus 1 by 2 dB by dt plus 1 by 3 dC by dt. This is how much will be the rate of formation of B and C. Okay. So from here I can get A naught expression will be equal to, sorry, AT expression will be equal to same as A naught e raised to power of minus K1 plus K2 into T. Okay, there is no problem in here. And which is the first instantaneous rate expression. Second, we need to find out what is the concentration of B with respect to C. Okay. Now, to find this, you notice what we have to do. 1 by 2 dB by dt, that must be divided by 1 by 3 dC by dt. That will give us K1 into A by K2 into A, the way I have derived it earlier. Hence, this will become dB, B by C concentration is equal to, this basically 3 will go up. Okay, so we will get this as 2 times of K1 by 3 times of K2. This is the expression which you will get. Okay, suppose if I asked you, let's say I put the third one, percentage yield of B. If I want to check percentage yield of B, then basically it is B divided by B plus C into 100. So I will do the same thing here. 2K1 upon 2K1 plus 3K2 into 100. Okay. Clear? Same way you can find out what is the percentage yield of C. Everybody clear on that? Now suppose if I add one more factor here, I need to figure out BT. How do I find BT? Here is very interesting fact. How do we need to judge this? Because A is basically giving 2B and 2C, 3C. So if this is A naught minus X and minus Y, this is basically will be 2X and 2Y. So I can't simply say this, right? AT is equal, A naught is equal to AT plus BT plus CT. This I can't say. But what I can say, that BT if you divide it by 2, CT if you divide it by 3, sorry, this is 3, then this will be correct. So this is the factor that we need to use here. So if you want to calculate BT, then you will take this AT, A naught is equal to AT plus BT by 2 plus CT. And CT we just got it. CT is equal to 3K2 by 2K1 into B. So 3K2 by 2K1 into BT. Okay. I think now you know how to calculate BT. From here we can get what is the value of BT, what is the value of CT. These expressions can also be asked to you. You should be ready to derive it. So this question is clear, everybody. Please do check. Oh, go ahead. 1 minute. See, instantaneous rate will be like this, minus dA, sorry, half of dA by dt. That will be the rate change, which will be equal to dB by dt plus dC by dt. That is equal to 3 times of K1, okay, into A, correct, plus 4 times of K2 into A. Got it? Now, if I bring this A to the left hand side here and take half to the right hand side here, so I will get dA by A minus, that will be equal to 6 times of K1 plus 8 times of K2 multiplied by concentration, sorry, multiplied by dt. Okay. Now, if you integrate this, you'll get dA by A naught to AT with minus, that is equal to 6K1 plus 8K2 into dt integral 0 to t. So basically, it's the same expression which you will derive as AT is equal to A naught e raised to power of minus K overall into t. But what is the K overall here? It will be 6K1 plus 8K2. Okay, so this is the important part to learn from here. This is about part one. Okay. Now part two is about concentration of B by C, and concentration of B by the ratio of B by C is equal to whatever be the ratio of K, right? So K ratio is what? 3K1 upon 4K2. That's it. This is what we need to use. Okay. Now imagine if you want to derive the B expression and C expression here, how do we write? A is giving, you know, B and C here. 2A is giving B and C here with 3K1 and 4K2. So if this is A naught minus X minus Y, now this will become X by Y, and this will become Y by, sorry, X by 2 and Y by 2, correct? And in such case, AT now will be equal to, can I call this as AT plus BT plus CT? No, I can't, but I can do the same when you multiplied BT and CT with 2 times. So this will be 2 times of BT plus 2 times of CT. Okay. Now things will come out to be correct. So you will be using this formula to figure out BT and CT. And B and C relation is like this. Okay. So I hope you understood. No matter how much generic way you can make the parallel reaction, right? You can always calculate, you know, expression of A, expression of B, expression of C, and also what is the ratio of concentrations. Clear? All good? Everybody, check. Let's learn what are sequential reactions. Got it? Check. Sequential reactions are those. So, reactant giving product. This will be the overall reaction. Reactant first gives an intermediate, then second step intermediate gives a product, and both are first order kinetics, which means A giving B, B giving C is always going based on the first order kinetic second inverse. Okay? So see, initially if the concentration of A is A naught and there is no B and C, then after time t, this will become AT, BT, and CT. Okay. Now notice one second. Now, if there is X amount lost from A and X amount formed in B, then from that same B, let's say some Y amount is lost and that is forming in the form of C. Then at time t, this will be the concentration of A. This will be the concentration of B and this will be the concentration of C. The rate of change of A can be written as K1 into A. So AT can be A naught e raised to power of minus K1 into T. Okay. And you can see R1, which can be written as K into A raised to power of N in general, right? Okay, for nth order. And now notice, how do we write the rate of change of B? Rate of change of B can be written as there is a certain amount of rate that is helping in formation of B. There is some rate which is helping in loss of B. So you can see K1 into A is the rate at which it is forming. K2 into B is the rate at which it is losing out the rate. So net rate will be K1A minus K2B. Correct? This will be K1A and K2B. Now notice this one thing here. One second. Let me just delete this part of it. Okay. Let me just delete this part. It's irrelevant now. Yeah. Check. Focus on this part now. Check. dB by dt is equal to K1 into A minus K2 into B. So multiplying exponent of K2 into T on both sides. So dB by dt into e raised to power of K2 into T. That is equal to K1 into A can be, A into e raised to power of K2 into T minus K2 into B raised to power of e raised to power of K2 into T. I can take this to the left hand side. Then I will get this expression on the left hand side, which is equal to K1 A raised to power of A into e raised to power of K2 into T. Now have you noticed this one? This is same as differentiation with respect to T of two variables. One is B and the other one is e raised to power of K2 into T. Correct? Because if you differentiate that with respect to T, you will get the same expression. Notice this is like d of dx into uv, isn't it? So if you differentiate that, we'll get dB by dt into e raised to power of K2. And second time, keeping the B constant, you have to differentiate this one. So K2 into e raised to power of K2 into T. So d by dt of this is equal to K1 into this. Okay. Because now I'm writing this A in terms of A naught. So I will get this as K2 minus K1 into T. Now if I integrate this with respect to 0 to B concentration and 0 to T here, so I will get B into e raised to power of K2 is equal to this entire thing. Okay, because exponent of K2 minus K1 into T is equal to exponent of that divided by K1, K2 minus K1. And now if I substitute that 0 to T here, so B into e raised to power of Kt is equal to K1 A naught by K2 minus K1. And this will become e raised to power of K2 minus K1 K1 into T. And once when T equal to 0, that will become 1. And now take this e raised to power of K2 into T onto the right hand side. So now we'll get B is equal to K1 A naught by K2 minus K1 into e raised to power of, here K2 will get cancelled. So minus e K1 into T and minus exponential minus K2 into T. So this is the expression which you will get for B. Now to derive the same thing, you will get similar term for C also. Okay, because I need to write K2 into C. So sorry, this will be K1 into K2. K1 into K2 and A naught K2 by K1 into this entire thing. So this will be the expression of C. Clear? So this is C, this is B, and we already got the A. Concentration of A is equal to A naught e raised to power of minus you can see here K1 into T. Right? These three are the expressions for the uh, sequential reaction. All right. So quickly go through it once. Check out how we have derived it. This is a very standard question which is asked in series reactions. That is, Find the time taken for maximum value of B. Okay. Why is that maximum value of B is being asked? Now notice one thing graphically. In a sequential reaction where we are going A to B to C, so A will continuously decrease. Okay. So B, because it will start increasing initially, slowly start giving C. To certain extent, it will start increasing. Thereafter, the rate of A will drastically decrease. Then the concentration of B will start decreasing. And C will continuously increase right from the start. This is how the C will start changing. Okay. So that means B at some point of time it will reach to its peak value. Then it will start coming down. And this is a time that has been asked. What is the T max? T max is the maximum time taken for reaching the time taken for reaching the maximum B value. Not maximum time, it means time taken for maximum of B value. So let's see how we can do that. We know we learned that this expression of B, so which means concentration of B with respect to T would go like this. And moreover, so at this point here, you can see there is a maxima. If there is a maxima, we know that dB by dt must be equal to 0. So differentiate this factor. So what do I get? I will get this as K1A by A naught by K1 minus K2 into exponential of minus K1 into T by minus K1 plus, sorry, minus e raised to power of minus K2 into T by minus K2. That should be equal to 0. So which means if I take this minus out here, so I will get this as e raised to power of minus K1 into T is equal to e raised to power of minus K2 into T. Correct? Because rest all things, sorry, by K1 and by K2 into T. This is what I'll get. So which implies if I take this exponential factors and one direction, so I will get e raised to power of K2 minus K1 into T. Correct? K2 minus K1 into T is equal to K1 by K2. Now take ln on both sides. So what do we get? Ln e raised to power of K2 minus K1 into T, that is equal to ln K1 by K2, which implies K2 minus K1 into T max. This is the one which you are trying to figure out. That is equal to ln K1 by K2. Hence, T max will be equal to ln K1 minus ln K2 upon K2 minus K1. So this is the value which you will get. This is T max. Please check everybody. This is a very standard question. It will be asked to figure out what is the T max in this case. Done. I guess this is not a big deal. Should be able to do that. Check. Now, like I said, A is giving B and B is giving C. These are happening at different rate constants, K1 and K2. Now, let me tell you, if you go from A to B, suppose if you are going from A to B here, correct? We know that concentration of A is decreasing. So definitely this will decrease quite exponentially here. So this is the way concentration of A is decreasing. But you know, there are two things we can offer. If suppose this K2 value is very high than K1, which means the rate of change of B towards C is very fast. In that case, whatever the B initially is forming, before it reaches to a very high concentration only, it will start losing out towards C. So what happens? The T max which you will receive will be at a very sooner value, and the concentration, the maximum concentration of B which reaches will also be not very high value when K2 is far greater than K1. Okay. Similarly, if K1 is far greater than K2, in that case, A is drastically decreasing. Okay. And because K2 value is very small than K1, B will accumulate to a large value. So to a large quantity, B max will reach. So this will be B max. Okay. And this will be the T max value here. Okay. And from there, it will start decreasing. C anyway will start constantly increasing in this case. Clear? C value will constantly increase in this case. Clear? I hope this part is clear. Graphs have been a very standard question. So you should know how to realize the graph, in which case how K1 and K2 are related to each other. Okay? Done? So guys, this is how much theoretically you need to know from this topic. Got it? So before solving rest of the questions, there are two, three more theoretical points which are mainly asked from advanced point of view. Let me just take that points as well. Okay? Clear? Right. So, okay, is the graphical representation. Okay, graphical representation of K versus T. That is rate constant K versus T. Okay. So we know that from Arrhenius equation, from Arrhenius equation, we learned that K is equal to A e raised to power of minus EA by RT. Okay. And this is what we call it as. Okay. Let me call this as an integrable form. Let me put it this way. Okay. So what I'll do, this is the formula which we know. Let me write it in terms of log. So ln K is equal to ln A minus EA by RT. Correct? Now, if I differentiate this with respect to K, correct? So, if I write this as dk by dt, okay? I mean the first formula here, if at all I differentiate that, so what do I get here? dk by dt will be equal to, this is a temperature, sorry, dk by t with respect to temperature. Then I will get this as A e raised to power of minus EA by RT into EA by RT square. Correct. That minus will be compensated with it. Correct. So now this is a differential form. This is the differential form. Okay. So now dk by dt, don't pull harder. dk by dt is equal to k into, because this entire thing is again k only. So k into EA by RT square. Now can you see this is a positive value? This is greater than 0. A positive value. That is, the first integral is a positive value. Now let me differentiate this once again. Correct? If I double differentiate that, I will get, go to the expression again, A e raised to power of minus EA by RT into EA by RT square was already there. Now I need to differentiate that. Oh, sorry. I can't do that. Sorry. Because it is in a U into V form. So that means I have to differentiate separately. So this into, if I differentiate this one, it will be EA by RT cube into minus 2 plus, don't do that, A into EA by RT square, and then I have to differentiate this exponential form, which is e raised to power of minus EA by RT into EA by RT square. This is what we will get. So again, this entire thing is K. Here also we got this as K value. So I will get this as K into minus 2 EA by RT cube plus EA square by RT raised to power of 4. This is what I'll get. So from here you can see I can take this common. K into EA can be taken common and RT cube can be taken common. So I will get this as minus 2 plus EA by RT, isn't it? This is the value which I'll get. Correct? Now here we got these two factors here. One is if d square k by dt square, correct? If this has to be greater than 0, which implies t has to be less than EA by 2r, correct? And if d square k by dt square, this has to be less than 0. If this has to be less than 0, okay, then when t has to be greater than EA by 2r, okay, which means have we noticed that at this particular value of temperature, we are getting a point of inflection, that is concavity is changing, right? Hence, you will notice that the graph would go something like this. So if I plot K versus T here, the graph will go this way. Sorry, let me write it properly. Like this. And let's say this is the point of inflection. So at the point of inflection, the value will be EA by 2R. So remember, the K increases with temperature, correct? But how does it increase? This is the way it will increase. Clear, everyone? So this is a basic differentiation only. I do not think we should have much problem about it. So please check it out. If anybody has a problem still, please let me know.
Sir, you are muted.
Oh, sorry, beta. My mistake. Okay. Let me tell you. I was trying to explain how the graph of ln k versus 1 by t is. Okay. So ln k versus 1 by t, this is the formula ln k. and you know the variation. And in this variation, you can see the numerator has a differential value, denominator has a multiplication value. Hence, the effect of increase in rate will be more at a lower temperature as compared to that of higher temperature. And if you notice the activation energy, if let's say in one equation A to B, activation energy is higher than in the other equation A to B. In that case, if you are increasing the temperature, then the case where the activation energy is higher, there the rate will increase more faster. So you can see K 310 to 300 will be greater than K 310 to 300 in the first case as compared to the second case. And that can be plotted like this, beta. ln K versus 1 by T. The first case will be like this, second case will be like this. The third aspect is about increasing its temperature. On increasing temperature, usually the mu value decreases because the ratio of K2 by K1, that value decreases at higher temperature. That is, if you are changing 300 to 310 or 400 to 410, then the mu value here versus the mu value here, if you compare, at low temperature, the mu value will be higher. Okay, these are the important application points from uh, rate constants. So please check.